Swayam Prabha. Digital India. Educated India.
Well, we have so far discussed about what are the sources of strength under room temperature or relatively low temperature conditions, and when we talked about heat treatment, it was just about heating it to a certain temperature and cooling it at a certain cooling rate, just to change the microstructure, just to change the organization of the alloying elements which were added to the material. So, it could in case of steel, it could turn into either pearlite or bainite or martensite depending on the cooling rate. Now, when we talk about heating the material and maintaining it at high temperatures for prolonged period of time in service, the picture is completely different. That is because the material not only undergoes microstructural changes, but it also results in different rates of deformation. So, that is what is called as creep, which is time, temperature, activation energy dependent phenomenon, particularly when metals are subjected to prolonged heating and loading as well. For instance, you take boilers. Boilers are subjected to heating, they are maintained at a certain temperature for a prolonged period of time, and there is internal pressure acting on the material, which is sustained over the entire duration of operation. So, this subjects the material to a phenomenon called as creep, which is where the deformation depends upon time, the extent of exposure, the extent of duration of exposure, the temperature, and the corresponding material property, namely the activation energy. So, we will see today how temperature comes into play and it interacts with the microstructural features, basically defects. I told you that strength of materials is all about managing defects. So, now when the temperature comes into play, it influences the defects in different ways, and therefore, management of defects becomes a completely different ball game altogether. So, we have a typical creep curve unlike a tensile curve. So, supposing you were to apply a constant load or therefore, an initial constant stress, then you have some instantaneous deformation taking place here. So, you plot the creep strain at on the y axis and time here. So, unlike a tension test where we plot load versus elongation or stress versus strain, here we are talking about creep strain versus time. The reason being that it is a time, temperature, activation energy dependent phenomenon, which means that the time is an extremely important parameter. That is because creep as a phenomenon is significantly influenced by diffusion, and diffusion is a time, temperature, activation energy controlled phenomenon. So, that is the reason why we when we study creep, we look at the creep strain and relate it with time to find out whether the strain rate remains constant, whether the strain rate is increasing instantaneously, because when the strain rate increases, the rate of depletion of cross section increases, because this is all plastic deformation, permanent deformation. So, if the strain rate increases very rapidly, then there is a rapid rate of depletion of cross section, and therefore, the stress rate correspondingly increases, and the material being soft as well as material permitting diffusion of atoms, will result in a very rapid reduction in the cross sectional area. So, that is what is indicated over the curve over here. There is some instantaneous deformation when the material is loaded. So, that the creep strain increases. So, here the creep strain rate is practically infinite because everything is instantaneous. After that the creep rate goes down because the dislocation activity being present, and the creep rate goes down, and at a decreasing creep rate finally we have what is called as a steady state creep rate. So, steady state creep rate occurs at an increasing strain rate, but at an increasing strain, but at a constant strain rate. So, here the strain rate is infinite, then it continues to decrease, and it decreases to a point where it becomes a steady state strain rate, and then it goes on to increase very rapidly. So, you have three regimes of creep, namely primary, secondary and tertiary. In tertiary creep, it is kind of runaway type of situation where the material would get deformed under enhanced strain rate and finally end up in the rupture. That is because as the strain rate increases, the depletion of cross section increases. As the depletion of cross section increases, the stress rate increases, and therefore, the material very rapidly moves towards rupture. So, this is the tertiary creep rate, which is usually avoided in all applications. So, what we are interested in is the secondary creep rate, and this is the only useful regime when we talk about service conditions of a product or service life of a component. So, lower is the secondary creep rate, larger is the life under creep type of deformation. So, one has to take into account this creep. For example, you have a turbine blade which is being subjected to a high temperature and high pressure. So, now very high pressure will be acting, generating a large amount of stress. So, there will be some creep deformation taking place over a period of time, and if the creep deformation takes place significantly, then it will also significantly change the geometry of the turbine blade, and therefore, the turbine blade will have to be discarded after a certain change in the geometry, because it will cease to serve its purpose. So, the creep rate has to be extremely small, the strain rate under creep has to be extremely small, so that the duration for which the component can serve under high temperatures is long enough. So, that is why people want to know as to at what point of time, after how many years or how many decades will the component cease to serve its purpose, will go out of shape. Why? Because it was subjected to consistent high temperature as well as consistent high stress. So, under these two things, under these two conditions, the material deforms at a very slow rate, but then the deformation being cumulative and permanent, it results in a permanent change in shape of the component over a period of time, and beyond a certain limit the component ceases to serve its purpose. So, that is why people would like to understand the different mechanisms of creep and which mechanism would be prevalent under what service conditions, and how to arrest creep to the extent possible, so that one is in a position to get service from the component for longer durations, meaning the life of the component is increased. So, you have initial very high strain rate, then there is a relatively slower strain rate, again followed by a very high strain rate, and so this is the region of slowest strain rate that is of interest to us from service conditions point of view. Now, this creep rate therefore becomes an engineering design parameter which is always taken into account while designing any product that is subjected to high temperature and stress. So, if you take a nuclear power plant or any power plant or thermal power plant where the pressure vessels are subjected to high temperatures and high pressures, this issue of creep is going to arise. Now, when failure or too much strain are not the options, so it is very important that the material should not get subjected to too much strain. So, it may not split into two, it might not explode, but even if it is deformed over a large amount of strain, still the material would have failed. So, that is the reason why we need to study creep very closely. So, these are the expressions which give you the expression for steady state creep, which is equal to K1 sigma raised to n. So, it is a non-linear relationship between the stress and the strain rate, and therefore, one needs to have a rupture. So, this will be this is the stress is plotted against the rupture time, and you see that as the temperature increases, the rupture time also tends to decrease, and for a given rupture time, the workpiece is able to sustain a much lower stress at increasing temperatures. So, as you see here, as the temperature increases from here to there, the for a given rupture time, it is able to withstand a much lower stress. So, as the temperature of service increases, the rupture time also tends to come down very significantly. It does rupture. That is because for some time it will remain in this air region, but then as the stress increases, of course the time increases, the strain rate will increase and finally end up in rupture. If you look at this graphs, you have steady state creep rate. So, here you have certain steady state creep rate, and then the as the temperature increases, the stress that will cause the same steady state creep rate also decreases. So, the stress goes down, and therefore, the steady state creep rate is related with the temperature, stress and activation energy by this expression. So, it is K2 sigma raised to n exponential minus QC by RT, where Q is the activation energy of the mechanism of creep that is operating at that point of time. So, for instance, you have diffusion as the main mechanism, then QC will be the activation energy of diffusion. If there is something else, some other mechanism that is operating to cause creep, then the activation energy will pertain to that particular mechanism. So, these curves pertain to low carbon nickel alloy. So, now if you take the effect of various parameters on this, you see that here there is a sudden rise in creep strain, and then there is a gradual reduction in the creep strain rate, after which it is constant. So, practically below 40% of melting point, below homologous temperature of 40%, 0.4, you do not have any creep at all, because now you have the creep strain which is sustained. So, there is no effect of temperature as long as temperature is less than 40% of the melting point, whereas when the temperature is more, as the temperature continues to increase, then you have a steady state creep rate which is which increase strain rate is constant, but the creep strain continues to increase under creep. Here the strain rate is 0, the creep strain rate is 0 because there is no change in creep strain with time. So, naturally the strain rate is creep strain rate is exactly 0. So, at low temperatures we do not experience this, but at relatively higher temperatures we experience this. What is the reason for this? There are many possibilities or many issues here. Once the temperature comes into play, the grain boundaries are the ones which get affected the most, because temperature increases the mobility of atoms, and since the grain boundary is the region of the maximum disorder, the maximum effect of temperature falls on the grain boundary, and therefore, the diffusion of atoms is much faster at the grain boundaries. So, gradually the grain boundaries tend to become weaker. The grain boundaries are the ones which were strong at low temperatures, but now the grain boundaries tend to become weaker because the temperature is rising. So, part of the mechanism refers to, so part of the reason why you have creep strain is because of diffusion taking place along the grain boundaries, due to which you have grain rotation and grain boundary sliding, and plus added to that some dislocations, dislocation movement also. So, here at high temperatures, which are more than 40% of the melting point, you do have some creep strain, which is well, at low temperatures, relatively low temperatures, it will be a slow strain rate, but a non-zero strain rate. So, you will have a non-zero strain rate here in a steady state condition, and then subsequently at a much longer period of time, you will find that it is rupturing. So, the time duration or the life of the component in terms of time is very high if the temperature is low or stress is relatively low. As the temperature increases, naturally the diffusion is faster, and therefore you have much greater creep strain, and therefore the life of the component also comes down that fast. So, when temperature or sigma increases further, the life is further reduced. So, one can schedule the maintenance of any equipment that is subjected to high temperatures, inspection of equipment subjected to high temperatures, so that the effects of creep can be taken care of and failures, in service failures, can be avoided. So, with these creep curves, one can, to start with, design a product that will last a certain duration. So, the life of the component subjected to creep is assured by design. Then you would monitor the creep strain from time to time over a period of time at based on the temperature and stress that is acting on the component, and then decide on its maintenance schedule. So, it is possible that the in service conditions for some reason lead to an accelerated creep or more creep strain than what was anticipated, and therefore you might have to monitor the creep rate. So, that has to be done under very critical applications like nuclear reactors and boilers, and basically pressure vessels operating at high temperatures. But then right at the design, if you have been conservative enough, then there is no there is unlikely any issue is unlikely to arise, and therefore you should be able to get the full service life of the component, which will naturally be replaced at the end of the service life. So, mechanism of creep, there are several mechanisms, and then they can operate in unison also, depending on the conditions congenial to their operation. Creep mechanisms involve stress induced vacancy diffusion. So, vacancies are the ones which diffuse. So, they get generated at the grain boundary, and then they diffuse across the lattice also, or in the grain boundary itself. Then there is dislocation motion, and then there is grain boundary sliding. So, there are number of mechanisms of creep, and so the stress induced vacancy diffusion is one. Then there is stress induced grain boundary diffusion is another, dislocation motion is third, and grain boundary sliding is the fourth mechanism. So, there are a number of mechanisms which are involved, and each leads to a different dependence of stress on strain rate. So, we have seen that epsilon dot equal to K1 sigma to the power n. So, the extent of non-linearity will depend on the kind of mechanism that is operating. So, typically depending on n, one can make out which mechanism is a dominant mechanism. So, typically let us say only one mechanism, let us say grain boundary sliding is in operation, then you will get one value of n. Supposing there is just dislocation movement, then the n is something else. You have only grain boundary sliding or grain boundary diffusion is taking place, you have another value of n. So, basically if you have one single mechanism operating at a given point of time, supposing you are able to do the test in such a way that there is only one mechanism operating at that in that domain of stress and temperature, then you will be able to gauge the operating mechanism based on the value of n. So, the creep mechanism for a particular material is identified by comparing its experimental n value with the values predicted for various mechanisms, and correlations have been made between the activation energy for creep, that is QC, and the activation energy for diffusion. So, QC is the general term for activation energy for creep, but then it takes the values depending on what kind of mechanism is operating. So, it could be QD or QG, maybe where QG could be grain boundary diffusion, then QD could be stress induced vacancy diffusion. You could have different kinds of activation energies, taking the QC taking the value of those different kinds of activation energies. Creep data is presented as deformation mechanism maps correlating stress, temperature and constant strain rate contours, because one is interested in identifying under what stress one should for a given stress what should be the temperature and what are the consequences of having that stress temperature combination. So, if one wants to reduce the rate of straining or rate of change of shape, then one has to use this deformation mechanism map and make sure that the mechanism that leads to minimum rate of strain, mechanism leading to the slowest strain rate remains operational. So, basically it enables you to select conditions under which the product should operate, so that the creep strain rate is the lowest. So, now we have given two parameters among stress, temperature and creep rate, and of course, once given the DMM, deformation mechanism map, one can read off the third parameter, and based on the characteristic value of that parameter, one can infer about the mechanism as well. Now, one problem with these creep tests is that since it is a time dependent phenomenon, particularly when the stress is low or temperature relatively low, where you have non-zero creep rate, but the temperature is not high enough to cause very rapid creep, it may continue for years for that matter. So, creep experiment can continue for years. Now, we are not willing to wait for that long. We need to gauge the properties of the material much earlier, meaning we need to accelerate the testing procedure. So, that is what we do by accelerating the creep rupture test. So, we start with a test to find out the creep properties, but then we do not wait for years, we do not wait that long to gauge the material behavior. For example, you take a boiler, it might not operate at as much higher temperature as a gas turbine, but then boiler definitely operates at a relatively lower temperature than the gas turbine, but it is still subject to creep by virtue of its temperature and internal pressure that it experiences. Now, a boiler is an entity that can operate for years together, and so you do not expect any significant creep deformation to take place over even a number of years. So, now if you have to test the material for creep and gauge its suitability for boiler application, you will invest one full lifetime before you can really arrive at one single conclusion. So, that is the reason why people do accelerated creep test to assess the suitability of the material for boiler or gas turbine or some such critical applications. So, you get short term creep data and extrapolate it to the long term. That is where the crux of the problem lies, that if we extrapolate this data from a short term creep test to long term. So, the accuracy of extrapolation is something which becomes a matter of debate, because how risky is it to use one particular model as opposed to another model when we extrapolate data. So, that is where we need to be careful. So, after a lot of experience, it has been found that extrapolation to in service condition is possible using what we call as a Larson-Miller parameter. So, that is because you have a combination of temperature, you have time to rupture, okay, and so you have this as a so called Larson-Miller parameter, which is plotted on the x axis, and on the y axis you have the stress. So, basically what it will give you is that under different stress values, what is the value of Larson-Miller parameter, which gives you a combination of temperature and time. So, if I have one particular value of Larson-Miller parameter, then for a constant Larson-Miller parameter, I can say that the either it can be this temperature and a particular amount of time, or a different combination of temperature and time, so that this expression remains constant. So, if we take one particular value of Larson-Miller parameter and we have a certain stress in MPa, which can be read off from this curve, then what we mean is that under this stress we have this Larson-Miller parameter. So, if the temperature is low, the TR will be higher, time to rupture will be more. If the temperature is more, TR will be less, because this has to remain constant. So, the behavior of the creep revealed by the creep curve is incorporated into this, namely that if the temperature is more, then for a given stress the time to rupture is less, and if the temperature is less, time to rupture is more. So, if we have to predict the time to rupture for a component that is subjected to a stress of 140 MPa at 800 degrees centigrade, then it turns out that so we have to first see corresponding to 800 degrees centigrade what is the Larson-Miller parameter. Accordingly, maybe so let us say it is 16, then we take that and then calculate the time for rupture. Now, this C, this constant in this expression is usually taken as 20. The time for rupture is in hours, and T, the temperature, is in Kelvin. So, this 800 degrees centigrade will be 1073 degrees centigrade, degrees Kelvin, 1073 degrees Kelvin. So, the corresponding Larson-Miller parameter for 800 degrees centigrade, and then stress is 140 MPa, 140 MPa. So, it is maybe somewhere here. So, we have roughly 24 as the, or close to that, as the Larson-Miller parameter. The temperature being 1073, C being 20, one gets the value of time to rupture as 9.7 days. So, now you see that the time to rupture is extremely small. So, compared to the creep life that is expected, the time to rupture is extremely small. So, what it means is that if we want to increase that time, we need to either reduce the stress to a much lower value and or decrease the temperature, so that we are able to get a greater rupture life. So, here is a problem which we can consider. So, a specimen 1015 mm long of low carbon nickel alloy is to be exposed to a tensile stress of 70 MPa at 427 degrees centigrade. So, you add this 273 to it, it will be roughly 700 degrees Kelvin, right. It will be close to 700 degrees Kelvin. Determine the elongation after 10,000 hours. So, 10,000 hours of operation. So, TR is T. So, we have to take TR as 10,000 hours and assume that the total of both instantaneous and primary creep elongation is 1.3. So, instantaneous and primary creep elongation is 1.3. So, that is the 1.3 millimeters. So, let us see how we solve it. So, you need to find out the Larsen-Miller parameter corresponding to this. So, capital T is 700 degrees Kelvin, then TR is the 10,000 hours, so log TR is given to be this, and the stress is 70 MPa. So, we need to find out the corresponding strain in the material, right. So, we need to find out the corresponding strain based on the so here for instance the strain is restricted to 1.3, right. So, we take that into account and determine its elongation after 10,000 hours. So, we need to use the strain rate expression there here, right. So, K1 sigma raised to n, and we can use these curves as well. So, once the activation energy is known, then you will be able to find out the strain rate, and based on the strain rate one can get the value of strain. So, then one compares it with that figure of 1.3 and checks whether the strain is going to be that much high or not. So, 70 MPa is the stress, and sigma is the value of n is required to be known, but then yeah, steady state creep data taken for an iron at stress level of 140 MPa is given here. So, epsilon dot s per, that is steady state strain rate at 1090 degrees Kelvin is given as 6.6 10 to the power 4 per hour. So, now the creep rate is given on an hourly basis. Okay. So, here if at 1200 degrees centigrade it is 8.8 into 10 to the power minus 2 per hour. If it is known that the value of stress exponent n for this alloy is 8.5, compute the steady state creep rate at 1300 degrees Kelvin and a stress level of 83 MPa. So, basically this data will enable you to get the value of sigma, and then see you have the this creep rupture test. So, you have been given the value of stress as 140 MPa, okay, and the corresponding value of Larsen-Miller parameter can be obtained from here, and using this data one can calculate the constants C and the constant K1 in the other expression and then solve this problem. Consider an 18-8 molybdenum stainless steel component that is exposed to a temperature of 923 degrees Kelvin. So, about 1200 degrees 923 degrees Kelvin. What is the maximum allowable stress level for rupture lifetime of 1 year? What is the stress level for rupture after 15 years? So, obviously, you are using this at 923 degrees Kelvin. So, the stress for rupture time of 1 year will be far too high as compared to the stress which can be withstood for 15 years. So, based on the stress and temperature conditions, the different mechanisms have been classified into the typical strain rate and temperature regimes. So, we see here that on this axis you have normalized stress sigma by G, and here you have normalized temperature as a homologous temperature. Now, below 40% of the melting point of the material, there is practically no creep strain, but then the normalized stress has been given over here, and therefore, you see that the normalized stress is extremely low when you have a relatively low temperature. So, practically there is no creep. So, this regime is called as Coble creep based on the inventors or scientists who propose the creep mechanisms. And at much higher temperatures, much higher homologous temperatures, and even at mild stresses. So, basically for creep, the driving mechanism is a temperature, because you need to provide the activation energy, and for that you need high temperatures. So, you have a Nabarro-Herring creep occurring at high temperatures, and the strain rates are relatively would be low, because the stresses, the normal stress is relatively low in this case. Okay. Then you have at higher normalized stresses, that is higher stress being applied, you have higher temperature power law creep. So, similar to our expression of k epsilon to the power n correlating stress and strain, here you will have power law creep, meaning you will correlate strain rate with stress. So, epsilon dot equal to k sigma to the power n. So, that will be the high temperature power law creep. And then in this regime where you have relatively low temperatures, but normalized stress is more. So, low temperature also you will get power law creep taking place. And then you have what is called a dislocation glide at much higher stresses. So, you see that the material softens, and therefore, even before the yield strength has been reached, the normal yield strength has been reached, creep deformation starts. That is because of diffusion taking place. So, at very low stresses, the diffusion in creep starts. Well, if your temperature is relatively low, and you have increased the loading, then you approach a situation of dislocation glide or dislocation mechanisms coming into play. Let us see the creep mechanisms. Now, a key typical characteristic of creep is its viscous response, in the sense that it is a non-linear response to a linear stress variation. So, you see that instantaneously the stress rises to a specific value, it is held constant for a given period of time, then it is dropped very rapidly, and then maintained at 0 condition or 0 level for a relatively prolonged period of time. Now, if you look at the strain in the material, it does not respond like what we would expect at room temperature. Under creep conditions, when you are at a temperature above say 30 or 40% of the melting point, there you will find that between 30% of melting point to 60% of melting point, the strain response is completely non-linear and not in tune with the stress. So, unlike a situation where the temperature is much less, less than 0.3 Tm, the stress and strain responses will largely be in tune with each other, but here the strain response is grossly out of tune because of the fact that there are viscous effects which play a role. So, it is lagging in phase. So, the response is lagging in phase. So, the stress does not rise directly to sigma dash, it gradually rises, and after a certain period of time it goes up to this particular level. Yeah. So, when you load the material, you load instantaneously, the strain like in creep curve, there is some instantaneous deformation, instantaneous strain. After that it rises very slowly, it becomes non-linear, and then finally goes to a particular strain value. Then when you release a load after, so this is time axis. So, after some time you release the load instantaneously, here also you get an instantaneous decrease in strain, but after that it is with time although the stress has become 0, the strain continues to remain in the material. Although strain rate large durations, after long duration might be very small, still that 0 strain rate is asymptotically reached. So, here you see that the strain rate is relatively high, and then gradually it becomes practically 0. So, what we see here is that irrespective of whether it is loading or unloading, the reaction, the strain reaction of the material, the strain in the material lags behind the stress. Okay? The strain response lags behind the stress response. Now, some creep mechanisms do not involve dislocation slip. So, that is what is very important, particularly in amorphous materials or non-metallic materials like glasses, ceramics, minerals, etc. Glasses, for example, basically it is a super cooled liquid, and therefore, in case of glass you would have an amorphous structure present, and therefore, there is no question of dislocations being present. In case of ceramics also it is an ionic bond, and so again you do not have any dislocation slip taking place. So, although these materials creep, the creep mechanisms have largely to do with the grain boundary becoming softer, diffusion taking place along the grain boundary, diffusion taking place across the grain. So, these are some of the things which will influence the creep rate in case of these glasses, ceramics and other materials. Depending on time, temperature, stress on and on the the QC, that is diffusion coefficient, stacking fault energy, etc. Okay, the energy parameter, you will find creep to vary, the creep rate to change. So, applications at high temperatures like steam turbines in power plant, jet engines, nuclear reactors. So, these need a creep limited design or creep dependent design. So, one has to take creep as a very important parameter or important design consideration, so that the cross sections can be designed so that the stresses are low enough to permit a large life or long life of the product. So, for instance, this is a light filament, and then you have this in an incandescent lamp. Now, this is made of tungsten. It is a coil filament of tungsten. Now, tungsten has got very high creep resistance, due to which you can use the filament for years together. So, there is some sagging, as you see here, some sagging has taken place from its operation over long periods of time. So, here even if you neglect thermal fatigue part of it, like the phenomenon of the filament being switched off and switched on. So, heating and cooling cycles, I mean even if we neglect that, still you have sagging taking place because of the fact that the creep sets in, and even if tungsten has got very high resistance to creep, the prolonged periods of operation result in this kind of sagging. So, this is an accumulated strain over long period of time, over several months of operation of the lamp. So, it is a light bulb filament which has sagged due to its own weight under creep. Similarly, a glacier also is subjected to creep, in the sense that earlier the water is frozen, and as the temperature rises, the same thing happens, like there is softening of the interior of the water, and so the glacier movement takes place. Very slow glacier movement takes place as in case of creep. So, we have this we construct this creep testing curve, and we have the primary transient, secondary which is steady state creep, and tertiary is the unstable creep. Okay. So, in secondary creep, what happens is there is a balance between strain hardening and recovery. So, the heat, the temperature results in recovery processes setting in. The dislocation density causes strain hardening of the material. So, the work hardening is caused by the dislocation density, and the recovery process results in softening or relatively large amount of strain. So, if there is no recovery at all, it is only strain hardening, then there will be no creep. Basically the point is there will be no creep, but then since the temperature softens the material and recovery sets in, then you have creep taking place over here. Then there is tertiary unstable creep where strain rate continues to increase, and then there is strain localization, formation of a neck, formation of voids, which results in rupture. Now, as you deform the material more and more, the entire microstructure is subjected to the stress. There are different microstructural elements having different magnitudes of ductility, different response to the creep conditions, and therefore, after a certain amount of deformation, certain amount of strain, there are voids nucleated at interfaces, there are discontinuities nucleated at the interfaces, and these discontinuities propagate over a period of time, and therefore, the strain rate increases beyond a certain limit of say constant strain rate operation, because that constant strain rate operation is a macroscopically constant strain rate operation. Internally, you might find that the non-uniformity in strain has a strain rate, and therefore strain has set in much earlier than what it was discovered macroscopically. So, that is the reason why in tertiary phase there is localization taking place, then there is internal coalescence of the intervoid ligaments taking place. So, these are events which finally contribute to the rupture of the deforming materials under creep conditions. So, as the cross section gets depleted, the strain rate continues to rise, and as the strain rate rises, the cross sectional cross section starts further reducing in magnitude, and the stress continues to rise. So, this becomes a vicious cycle, and due to that vicious cycle, the rupture becomes faster. Now, just one comment here, this creep curve was constructed at a constant load. So, the creep curve was so you had a constant temperature and a constant load. So, initially when it was loaded, it showed during primary transient relatively large strain, and then it settled down to one particular slow strain rate creep at that particular stress level. So, this we have seen already, but then if you look at the strain rate versus temperature curve at different stress levels, at high stress levels, of course, the range at which the creep rate would remain constant is reduced significantly. As you see here, at lower stress, okay, or at a higher temperature, the strain rate is maintained over a long period of time. So, a constant strain rate stays for longer duration, whereas if either stress or temperature is increased here, then you get a much smaller duration of constant strain rate regime, and the strain rate is also much greater than when the stress was less. So, if you see the three well defined stages of creep, low sigma at low temperature, there is no tertiary creep that is observed, because if you take low sigma and temperature is low, then there is no question of tertiary creep taking place. It is a normal plastic deformation that governs the failure. So, we have accelerated creep testing being deployed here. As you see, you have true strain rate versus true stress, and then there are different temperature values over here, and this is used for high temperature pressure vessels like boilers and so on, where you have certain creep rate, which is again very extremely nominal, a few microns per year or something like that. And if at that small level of creep rate, you will be in a position to operate the equipment without shutting it down for maintenance. So, prolonged operation of equipment requires the creep rate to be small enough. Aerospace industry, the aircraft has to fly for large distances, and it has to be in operation for months together or maybe years together. So, one should not have to take it out for servicing because the creep strain had been excessive or the creep phenomenon took place rather fast. So, that is why people carry out a stress rupture test right up to the rupture of the material. So, we carry out the test, and that is an indication of how sound the material is against creep. So, you have typically a straight line curve with the slope of the straight line changing at different locations. Okay. So, there are structural changes in the material, the microstructure changes, so new phases can form because of this diffusion phenomenon. New phases can form, for example, or grain shape and size can change, they can coarsen. So, there are many of these changes taking place. The grains may recrystallize for that matter. So, there are a number of structural changes due to which the slope changes, because the slope is characteristic of a particular microstructure. When the microstructure changes or a structure changes, the slope will change, because the mechanism of a creep also can change. So, we have seen what is the Larsen-Miller parameter, and so we have seen that TR is TR measured at a specific stress varies with temperature, so that PLM, that is Larsen-Miller parameter, is equal to constant. So, this is what we have seen. Now, unlike metals, polymers also show some symptoms of creep, but then in case of polymers, large part of the creep strain is usually recovered due to interaction with the chain molecules. So, we know that polymers are long chain entities. So, you have macromolecules of polymers. So, one macromolecule would be say one pellet of polymer. So, you have these chains opening up with stress, and with increasing temperature, these chains will tend to undergo again a viscous response, or it will give you a viscous response, something like this. So, it will increase instantaneous in strain, and then the strain rate will drop over a period of time. So, structural changes during creep include inhomogeneities in the material, because inhomogeneities in the form of discontinuities for that matter get developed. The main deformation processes at increasing temperature involves dislocation slip, subgrain formation, and grain boundary sliding. Now, dislocation slip is an indication that the grain boundary is still not all that weak. I mean, the grain boundary becomes weaker with increasing temperature, but then at some point called as the equicohesive temperature, the grain boundary and the interior of the grain remain almost the same in strength. So, this deformation would be around equicohesive temperature, maybe slightly higher than that. So, that you have some grain boundary activity, some activity at the grain boundary due to diffusion related processes. So, you have a coexistence of dislocation mechanisms as well as the viscous effects being generated at the grain boundary. So, subgrain formation and grain boundary sliding are the outcomes of the grain boundary becoming softer. So, when you talk about creep, strain rate per 1000 hours, okay, it requires just a strain rate of 1% per 10,000 or maybe 1 lakh hours of operation. So, that is the kind of strain rate that is expected in creep, because if it is more than that, then it means that the life is being exhausted that much faster. So, if you look at the structural changes in creep, we have dislocation slip, and there is deformation at elevated temperatures. So, there can be formation of compound, there can be formation of intermetallic phases, right, strain induced phases and so on, and then you have you have dislocation slip leading to subsequently to subgrain formation. Subgrain formation occurs at a large amount of a large dislocation density. So, as the dislocation density increases over a period of time, again this happens over a large period of time. So, then the dislocation density leads to subgrain formation, and subgrain formation results in formation of low angle grain boundaries, and so there is a possibility of easy climb and slip at increasing temperatures and formation of subgrains. Subgrain size depends on the stress and temperature. So, if you take large stress and relatively smaller temperature, then you will form relatively finer subgrains. If the temperature is large, if it is high temperature and stress is relatively low, then you will find that the subgrains would be bigger. So, low stress, high temperature, low strain rate produces large subgrains. That is what we have just said. Another mechanism is grain boundary sliding. So, there is a shear relative to these to the grain boundaries. You see here that one grain, there is a shear across the grain boundary, and due to that let us say this grain slides to a new position as shown by the dotted lines. Okay. Now, this will introduce some sort of mismatch at the end point. For instance, you have this triple point junction. So, now if all three grains shear with respect to each other or slide with respect to each other, you can create a discontinuity over here. Let us say all three grains are moving apart with respect to each other, then you will create a discontinuity at this junction. Similarly, the same thing can happen at this junction. So, movement of grains related to each other at elevated temperatures along grain boundaries is something that is called as grain boundary sliding, and lower temperature, lower strain rates and increased temperatures promote grain boundary sliding. So, at very low strain rates you have the phenomenon of grain boundary sliding that is present. So, here grain boundary sliding is something that is a high temperature phenomenon and never a low temperature phenomenon. That is because you need to make the boundary weak enough so that the strain is accommodated by the grain boundary. So, large amount of strain is taken by the grain boundary and most of the mechanism is diffusion. So, diffusion along the grain boundary. If grain boundary sliding was the only active mechanism, accumulation of material at one end of the grain boundary and deficit on the other. So, this is something which we need to understand, that there can be more than one mechanism operating. So, dislocation motion, diffusion, grain boundary migration also is another possibility. So, this is a very important aspect of creep, namely grain boundary sliding, where a material can accumulate at one end of the grain boundary and there is a deficit of material. So, here you will find that as this grain boundary has been sliding away on that side, you are likely to create a discontinuity over here. So, after of course, significant amount of strain, you get discontinuity generated, and then you beyond a certain limit you will have grain boundary fracture as well. In non-crystalline solids you have viscous creep. So, there are viscous fluids, or a viscous fluid is formed at the grain, or what one can say is that the disordered region of the grain boundary behaves as a viscous fluid. Okay. And so, that is how it becomes resistant, not resistant, it becomes sensitive to strain rate. So, more is the strain rate, more is the stress that is generated as a result of that. So, it becomes rate sensitive, and The thermal activation as in a diffusion process follows the Arrhenius type law, which is also used in creep deformation, right. So, these are in creep deformation you have time dependent movement of molecules or groups of molecules relative to each other under applied stress. Now, in contrast, creep in polymers is quite significant about the so called glass transition temperature. So, in case of polymers you have different regimes of deformation. You have what is called as glass transition temperature. So, this glass transition temperature makes the material behave like as soft as glass. So, the Tg of polymers is 100 to 200 degrees centigrade, and the creep is often observed around the room temperature itself. Then above Tg, hydrogen and van der Waals bonds are less effective, and molecular chains therefore are able to slide past each other. So, basically grain boundary sliding, intermolecular sliding also takes place because of relatively weaker bonding. Creep is easier in polymers with linear molecules, because these molecules are the outcome of the chains folding over and I mean over and over for a large amount of length. So, number of layers are created, and therefore you have when you have linear molecules, then these twist over or they get laid in a folded condition, so that the entire length can be accommodated. So, creep rate depends on sigma and temperature and is roughly similar to viscous flow. If temperature is sufficiently high and obstacles for sliding are relatively weak, then it will depend strongly on the viscous flow at the grain boundary. So, we will see how these grain boundaries and different mechanisms influence the creep rate, and how one can calculate or determine the activation energy for creep particularly is something that we will see in a subsequent discussion. Thank you.